All right, good afternoon, everybody. Thank you very much for coming. I appreciate there are a lot of good sessions out there, so thank you for making this one part of your day. The topic is a new service that we launched on Monday in gated preview called Amazon Verified Permissions, and specifically how you use Amazon Verified Permissions to manage permissions within your application. My name's Julian Lovelock. I'm the product manager. And I'll be joined on stage by my colleagues Amina and Mahmoud, and I'll let them introduce themselves as they take the stage. So, how's the day, or this particular session, break down? I'm going to do an introduction to the product, explaining why we built it, and a little bit about high level what it does. Mahmoud's going to get into more depth, talking about how you would integrate your application into this service. And then Amina will be talking about the Cedar policy language, which is the language in which the policies for this permission system are written. Like any good solution, it starts with a problem. So what is the problem that we were trying to solve? In a word, that problem is permissions. Or more broadly, how does an application developer manage the permissions within their application and authorize user actions based on those permissions? So whatever application you're trying to build, you have to have some element of permissions management within that application. If you're building an online banking application, you have to think about how do I determine which accounts different users are allowed to access and what transactions they're allowed to take on those accounts. If I'm building a photo sharing application, I have to think about who's allowed access to which photos, who can comment on them, who can create albums, etc. I'm building an HR system. I have to think about who has access to different employee records, who can access reviews, who can submit reviews, who can access payroll data. It goes on. So any application that you're building, pretty much, you need to think about how you manage the permissions within that application and how you authorize user actions within it. So we can define permissions broadly as the set of rules that describe what each user in the application is permitted to do. And we can express those permissions as policies. In the simplest sense, there are two types of policies: those that permit you to do something, and those that forbid your user from doing something. We also see in general terms two authorization models. There is what we often refer to as RBAC, or role-based access control, which works well in a hierarchical organization where users are divided into a group, into a hierarchy, and we can assign roles to different groups, and those roles determine what users in those groups are permitted to do. And that, as you might imagine, works well in a workforce environment where employees are typically organized into some sort of a hierarchy. The challenge that we often see with RBAC-based models is as you make those permissions more granular, you get more and more roles. And we have customers who've explained to us that they actually have more roles than employees. The other model is ABAC, attribute-based access control. This works pretty well in a consumer-facing application, where, as you might imagine, your users aren't divided into nice hierarchies. And so you're defining the rules in an ABAC-based model based on attributes of the resource that you're protecting or the identity that you're enabling access to, or for, I should say. Challenge with ABAC models is that they can become quite opaque, difficult to analyze, because these rules can come across as quite ad hoc. So if we've established that permissions management is a must-have, we can logically ask ourselves, well, how's it done today? So through the course of this session, you'll see various different examples thrown at you. My slides are going to throw an example at you that's oriented around a financial services application and begin to protect access to creating payees and actions like that. So we imagine a user of this online banking application needing to create a payee. And the application has to figure out whether said user is permitted to do this. And what we're going to see, more often than not, is that logic actually embedded into the code of the application. You can see there my attempt at code. You can see why I became a product manager rather than a developer. But you get the sense, which is that this code is going to have convoluted logic written into it that protects this particular transaction, but it's going to be part of the code. So what's the issue with that? Well, the issue is that in order to understand what or who is allowed to do what in this application, you effectively have to be able to read the code. Also, every time you change the rules around who is allowed to do what, maybe there's a change organizationally, maybe there's a new set of regulations, maybe there's an event that requires you to relook at the permissions rules within your system, these things all require you to go back and change the code of your application, which, to put it frankly, is suboptimal. And then the other thing is audits are difficult. It's not an unreasonable question for an auditor to ask, okay, who can create payees? And if answering that request requires the respondent to go look at the code, it's going to be a very lengthy and tedious audit. So we can begin to understand some of the characteristics that we want a modular permission system to have. We want those permissions to be expressed as relatively simple, easy to read policies. We want to be able to support role-based access control and attribute-based access control. And we want those policies to be auditable and easy to understand. If we look at it from a non-functional requirement perspective, we want very low latency because we're going to adhere to zero trust policy strategy. We're going to have our application check permissions for each and every time anyone within that application does anything, so that better happen quickly. It's got to be highly available because if the system stops working, then the users can't do anything in the system. And we want it to be easy to plug in because if a developer can't plug this service into their application, they're obviously not going to use it. So we've established we need a permissions management system. We know the kind of characteristics it has to have. Why can't we as a development team just build it ourselves as part of our application development? Why do we need to go to a third party and take a service from them to do this thing? Well, firstly, it's pretty time-consuming to build. It gets complicated quickly as you start to try and accommodate many different types of policies. And it's difficult to do right. There's some fairly complex mathematics that sit behind requirements like being able to analyze policies to understand who can do what, or if one policy contradicts another policy. If you want to be able to do that through some automated analysis tools based on automated reasoning. And Amina will talk a little bit more about that in her session, or her section, I should say. It may not scale. What you built to work well with 50 roles may begin to struggle from a performance perspective when you have 50,000 roles. And more often than not, governance takes a back seat. The logic of a permissions management system that enables you to go and see who actually created this policy? When did they create this policy? How come they were allowed to create this policy? Does the policy change? All of that governance layer is typically left out in a self-build. So this is where we'd like to introduce Amazon Verified Permissions as an off-the-shelf permissions management and authorization system that meets these challenges. Essentially, what the system does is to store permissions expressed as policies and provide a means for your application to manage these permissions and to authorize the users of that application against these permissions by evaluating those policies. I'm going to run through some high-level use cases, and then I'm going to hand over to Mahmood, and he's going to get into a bit more depth around these use cases. So we're going to imagine our financial services application. And we're going to want to start to think about, OK, as an application developer, how do I create and maintain policies in that application? How does a user of that application create permissions on the fly? Let's look at a use case for that. how does the authorization process work, and how do we go about auditing? I'm going to touch on these at a high level, and then, as I said, Mahmood's going to get into them in a bit more detail. So let's imagine our application developer. They're creating a financial services application. There may be a baseline policy that applies across all users of this application, such as allow the account owner not only to have access to the account and operate on the account, but also to delegate authority to a second user in the event that the account owner is not available. So this would be what we might think of as a baseline policy. It's created by the application developer as part, almost as an extension of the code of the application at the outset, and this policy is deployed along with the application. And you can see, or maybe you can't see, but there's an example here of such a policy. And as I said, Amina's going to get more into the structure of the policy language, but it's basically broken down into what we describe as a scope, which essentially caters to the role-based access control by defining a set of actions that a group or an individual user can take on a set of resources. And then there's a set of conditions underneath, which accommodates the attribute-based access control aspect, which puts qualifiers on those. Now imagine our end user, Jane, our CFO. She's taken a well-earned vacation, and so she needs to delegate access while she's away to be able to manage this account. So this is an example where an action by Jane within the application is going to result in a policy being created in the underlying policy store. In this case, a policy that gives permission to Jeff to manage the account, a specific resource, during the period of Jane's vacation. So that when our application end user, Jeff, logs onto the application and, for example, tries to create a payee on the account, the application calls verified permissions and says, I've got this user, Jeff. He's trying to take this action, create payee on this account, 515, can't remember what account, user 553, ... Is this permitted or not? And the permissions management system is going to come back with an allow or deny based on an evaluation of the policies. And this is all going to happen in a matter of milliseconds. Jeff is going to be blissfully unaware that his permissions have been checked, and assuming he's allowed to do it, he's going to carry on and create that payee. And then our final persona in this story is our auditor, who wants to have that view across all of the different, it's like the auditor's the most popular one to take photos of. I wonder why that is. Who basically wants to have that view across all of the permissions that have been created, who's basically benefited from using these permissions. And he's going to be able to do that based on a set of analysis tools that we provide as part of the product, as well as services like CloudTrail, to which audit logs are going to be written, and he's going to be able to use the normal CloudTrail tools to view those audit logs and see what happened. So at this point, I'm going to hand you over to my colleague, Mahmood. He's going to be walking through in a little bit more depth a sample application for you.
Thank you, Julian. Hi, everyone. Good afternoon once again, and thanks for being here. My name is Mahmoud Matouk. I am a solutions architect with AWS Identity. And in this section of the session, we will be looking at how to get started with Amazon Verified Permissions and what it looks like to build an application that integrates with this service. I will first go through a quick walkthrough into the console and the first few steps to get started. And then we will look at a demo application and few authorization scenarios and how to integrate with this from your code. So first, to get started from the console, the first thing that comes out is you'll be greeted with this screen and asked it to create a policy store. You can think about the policy store as a container of your policies. So if you have multiple projects, multiple workloads, probably with different authorization requirements, then you will be creating multiple policy stores. The policy store is a container, but it's empty. So you start filling this policy store with policies. And you can do this simply from the console by providing a policy description and then the policy body itself. We'll go into more details into the policy language with Amina. For now, this is a simple policy that allows a principal to access a resource as long as this principal is the owner of the resource. You keep adding policies and build your authorization model with multiple policies. You can do this using the console. You can do this using CLI, using APIs. So it could be also dynamic policies you create in your application in response to certain actions like sharing a photo or delegating to another employee or something like this. Once you fill your policy store or you create your policies, you can test the behavior of this policy store with some authorization queries. You can do this with a simulator that is built into the console. This helps you to troubleshoot how the authorization engine behaves, troubleshoot your data set, and so on. To do this, you provide these pieces of information, and this is also the same data that you provide to a query at runtime from the code. So you provide who's the principal, what is the action, what is the resource, and then optionally you can provide request context, which is a free-form map, things like runtime information, maybe the IP address of the source, the current time of the system, anything that is relevant to the policies in your policy store. The last piece of information is providing your data set. The data set is a JSON format that tells the engine what are my entities and what are the relationships between these entities. For example, if I ask the engine, is Bob authorized to view the image.jpg, I have to tell the engine who's Bob, what is an image, what are the attributes of these entities, and how they are related to each other. So the engine resonates over this data using the policies in my policy store and tells me if it's allowed or denied. The simulator tells you the decision. This is an allow, and if it's an allow, what was the satisfied policy? And if it's a deny, because just there is no satisfied policy, it will be a plain deny. If it's a deny because of errors in your data, like missing attributes, you are trying to compare certain attributes that are not provided as part of your entities, it will also tell you these errors. So you can either think that this is expected, this is how I designed it, or if this is not expected, then you go back and fix your data sets or change your policies as needed. This is all part of the development of your authorization model. This is what you do from the console to get started. As I mentioned, same thing can be done from the APIs and the CLI, so this can be baked into your CI/CD. It could be dynamic actions in your application as needed. So once I build my policy store, how do I use this at runtime to make authorization decisions in my app? We will look at this next, and for this, we will take Onyx to the vet clinic. I'm going to use a sample application that simulates the vet clinic portal. Onyx was always known for eating things he's not supposed to be eating, and he just got sick, so we need to take him to the vet. What is the scenario we are looking for? Dave is Onyx owner, and he needs to take them to the vet. So he contacted Sally, the office administrator of this vet, to schedule him for an appointment. Sally put him up for an appointment with their primary doctor, Dr. Jane. Because Dr. Jane is the primary doctor for Onyx, she has access to his history and the records of his previous visits. But she found that Onyx needs an X-ray. So she will refer them to a specialist, Dr. Adam, who will run the X-ray. And with this referral, Dr. Adam gains more access into Dave as a client and Onyx as a patient. They use this patient portal application, and we will be looking at a few of these use cases and how this translates into policies and how do I evaluate these policies at runtime. The first use case is fairly simple, so viewing client data and scheduling an appointment. As we saw, there are different personas in the system, and every persona has different permissions. Let's first take a look at the demo or the scenario, and then we can go back to the drawing board and look at our policies and how we structure them. Dave is the client. If he signed into the patient portal or to the clinic portal, he can see his record and information. He's allowed to view his profile. So if he attempts to do this, this is an allowed action, no issues. But he cannot schedule an appointment for himself. If he does this, it will be denied. And if he tries to refer himself to a specialist, this will also be denied. It is not his job. He has to go through the office administrator. So we saw 3 actions: viewing information, scheduling appointment, and referring a patient. 1 was allowed, 2 were denied. The next one is Sally accessing the portal. She's the office administrator, so she sees a more expanded view of all clients in this clinic. She's allowed to view profiles of these clients, and she's also allowed to schedule appointment, but she cannot do referrals. So we'll see that the referral action is denied for Sally, but if she goes back and attempts to schedule appointment for Dave, she should be able to do that. So how this translates into permissions. We have permissions rules, and we want to translate these permissions into policies. The first rule says I want to deny all actions across clinics. So let's say this clinic portal is used by multiple clinics. I want to make sure that no cross-clinic access is ever allowed. And I can do this with a forbid statement that says forbid everything when the principal.clinic ID doesn't match the clinic ID of the resource. This is a safe check in my system that this will never happen. The second rule says allow clients to view their own records. And this can be mapped as a policy that allows principal, who's a type client, to take an action client get on a resource that is also a client as long as the principal matches the resource. We will learn later that there are different ways to write the policies, and there might be things that are more optimized than others. So this is just an example of a possible way to map this rule. Keep in mind, I keep adding these rules to my policy store, as we saw, either from the console, from CLI, or whatever. The next permission rule says allow administrators to view client records and schedule appointments. And this can be mapped using a policy, a pure rule-based access control policy that says allow office admins to take actions like client get and appointment post on all clients. This is purely rule-based access control because the permissions are given based on the rule of the principal. And the next one is allowing primary doctors to view records of their clients and refer them to specialists. This is a mix of a rule-based access control and attribute-based access control. It's a rule-based access control because it applies only to principals who are doctors. And it's attribute-based access control because it has a condition that has to match attribute between the principal and the client or the resource. So I keep adding these policies to my policy store. Let's look at another use case, and then we will go back to how do I do authorization decisions at runtime and what my application architecture looks like. In this use case, Dr. Jane is going to refer Onyx to a specialist. So let's take a look at the demo first, and then we go back to the permissions. First, if I log in as Dr. Adam, who is the specialist, at this time, Dr. Adam has no relationship with Dave whatsoever, so he cannot view the client information. He cannot, of course, schedule appointment because he's not an office admin, and he cannot refer them. So all of the actions are denied for Dr. Adam at this time. If I log out and try to log in as Dr. Jane, who is the primary provider for Onyx, Dr. Jane, because it's the primary provider, should be able to view the record of their patient. This is an allowed action, and she should be able to refer them to a specialist. So she will submit a referral to Dr. Adam and ask for an X-ray and set the time bound for this referral to 3 months. Now, this creates a dynamic policy in the policy store that allows Dr. Adam to access the records of Dave and Onyx. So if Dr. Adam signs back into the portal, he will be now able to view the record of Dave and Onyx. So what happened behind the scene? We have a rule that says allow specialists to view client records during referral period only. So this is a time-bound, and it's dynamic. We can do this with a dynamic policy that my application creates in the policy store that says permit principal that is also a specialist to take an action client get on all clients when, and then you become very specific with the policies. This applies to a specific principal, who's Dr. Adam, a specific resource, who's client Dave, and only within this timestamp, only as long as the query time is before this timestamp. You can use the same scenario for many use cases like delegation, elevated access, sharing data between resources, and so on. So what does the application blueprint looks like? So we saw 6 policies. I added these 6 policies to my policy store. How does this web application make authorization decision at runtime? We look at one pattern, but there are many others. For this, I have my client application on the left-hand side. This is the web application. It could be a mobile application. I have my back-end APIs on the right-hand side. These are the back-end of the vet portal. And then I have API gateway in the middle as the access point to these APIs. I have Amazon Cognito at the top, which acts as the identity provider in this case. As we saw in the demo, everything starts with a user signing in. I have to know what is this user entitlements, what are their profile attributes, and so on. And then I have Amazon verified permissions at the bottom, and this is acting as the authorization engine. The flow starts by user coming into the application and signing in with Amazon Cognito. You can optionally federate. So it's a common scenario that I want my public clients to have a username and password, but I want my employees to sign in with their enterprise credentials, so you can do that. after signing in, Cognito issues tokens to the application. These tokens are signed, it's tamper-proof, it has the entitlements and group membership and data about the user, and you can also inject some runtime information, like what is the insurance status of this client, and any additional information that is relevant to your authorization decisions. Every API call that is made then from the application carries this token for authorization, simply adding it to the authorization header and sending it to API gateway. API gateway uses a Lambda authorizer to evaluate the decision. Lambda authorizer does 4 things: verifying the token, formatting a query to the authorization service, running the query and getting a decision, and enforcing this decision by returning an allow or deny to API gateway. Once the decision returns to API gateway, if it's an allow, API gateway just forwards the call to the backend. If it's a deny, then returning unauthorized error to the client. This is one sample architecture. It's a serverless architecture. Of course, you can remove API gateway and both AppSync. You can remove this layer and both your custom APIs and containers, and you can run the same authorization logic in your application if you want to. So now let's take a closer look at my Lambda authorizer, because this is where the integration with Amazon Verified Permissions happen. In my Lambda authorizer, I want to answer the question of whether the principal that is trying to make the call is authorized to make this action. To put this in a more technical way, I want to run a query that says, is Dr. Jane allowed to take the action referral post on the resource client Dave under these runtime conditions? To do this, and this is a sample Python code, I have 4 steps here. The first step is retrieving the token from the authorization header and just verifying it. This is a standard JWT token verification using the public key of the issuer. The second part is formatting a query to Amazon Verified Permissions. In this query, I have 6 important information. The first one is the policy store. What is the policy store that you are running this authorization query against? As I mentioned, you can create multiple. At this time, at the gated preview, you can create only one, but long term, you will be able to create multiple policy stores. So which policy store you are running this query against? And then the second piece of information is who is your principal. And this is information that is driven from the token. The next one is what is the action. And the action can be coming from the API context. What is the resource path you are trying to access, and what is the action? Is it a post? Is it a gate? Is it a bot? And so on. And as I mentioned, this is one pattern. You can think about unlimited patterns that you can have mapping in your application and so on. And number 4 is the resource. The resource could be identified as a resource path, a path parameter, a query string, a header that is in the API call, so you can derive all of this information from the API context and put it in your query. And then the next one is optional context. As I mentioned, this is a free-form map. So in this case, I'm providing what is the query time, what is the current time of my system. And then the last one is the data set, which tells the engine who is Dave, who is Jane, what are their relationships, what are their attributes, and so on. The next step is to run the authorization query with the service, and this is as simple as making an is-authorized call against the service client. Amazon Verified Permissions is just a service like the rest of AWS services. So you create a client using the SDK, and then you run APIs against this client instance. Number 4, you got a decision from Amazon Verified Permissions, and now you are trying to analyze the permissions and see what was the decision. Is it an allow or deny? And then number 5 would be enforcing this by returning a policy from the Lambda authorizer that says allow this call or deny this call. This is fairly simple, and we can take a few takeaways from the code. Now, this is your authorization logic. This is your logic in the code. It doesn't matter whether you have 3 actions or 300 actions. It doesn't matter if you have 10 user types or 100 user types. This code doesn't change much. Like, the code can stay the same. And all of the authorization decisions is offloaded to Amazon Verified Permissions. The other point is that by offloading this to a managed service, you don't have to worry about the operational heavy lifting and the scale and the high availability of the service behind the scene. You just make authorization decisions and enforces them at runtime. With this, I'm going to hand it over to Amina to talk more in depth about the Cedar policy language and the authorization engine behind the scene.
Thank you. Hello, everyone. My name is Amina. I'm a senior principal applied scientist at AWS, and I'm a member of the team who designs and builds the Cedar language. This part of the talk is going to be a deep dive, a technical deep dive into our design and development process, and we're going to talk about what makes Cedar unique in the space of authorization languages that you're going to find today. So Cedar is a new domain-specific language designed specifically for authorization, and it comes with batteries included. We have an ergonomic syntax and semantics, we have a fast and safe runtime, and we have powerful static analysis tools. Because authorization is critical to security, we have built Cedar to a high standard of assurance, using techniques such as automated reasoning, theorem proving, and differential random testing. Now, before we dive into the details of how we did this, let's talk about what it takes, what's challenging about building something like Cedar, and why we decided to take on this challenge. In order to build a robust authorization solution, so a language and a runtime, you have to solve three big problems. The first problem that you have to solve, the core challenge, is designing your language. In particular, deciding what constructs to include in your language so that it is expressive enough for policy authors to say what they need to say, while at the same time being restricted enough to allow us to bound performance latency and to provide static analysis tools. Some choices here are obvious, right? You probably don't want to include loops in your authorization language. If you include loops, you're not going to be able to bound authorization times, right? And in the worst case, policy evaluation may not terminate. Some choices are less obvious. For a language to be useful, it has to include some sort of an aggregate data type, right? So think lists or sets. But what data type you include and what operators you provide on those data types is going to determine your ability to write tools that can reason about policies automatically and prove properties that users care about, such as that a policy never allows access to a private or a sensitive resource. Okay, so suppose that you have done this right. You have chosen the right constructs, you have constrained your language appropriately. The next thing that you have to do is actually build a language. Authorization is critical not only to security, but also to performance. So your engine has to be both fast and safe. And safety here means that it has to correctly implement the semantics of your language, the spec that you're giving to your users and that they're relying on. Some choices here are obvious too. For example, you don't want to build your language in a low-level language like C, all right? Your engine in a language like C. The reason is that C will give you speed, but it's going to be very hard to prove safety. On the other hand, you probably don't want to build your engine in a high-level, purely functional input language of a theorem prover. If you do that, you're going to be able to prove safety, but it's going to be very hard to get good performance. So how do you get the best of both worlds? How do you build your engine so that it's both safe and fast? And finally, even if your language is well designed and your engine is safe and fast, it is still possible for people to make mistakes when they're translating their intent into policies in your language. For example, you can write a policy that's actually okay. It does the right thing on most inputs. But on a few small corner cases, it does the wrong thing. It either permits access when it shouldn't, or it denies access when it should. Now, to find those corner cases, conceptually, your static analysis tool has to explore an infinite state, okay? So the set of all possible requests that could happen, and the set of all possible states of your entity store. How do you write such an analysis so that it's fast, it can actually reason about this infinite space, and it's precise? All right, so hopefully this discussion has convinced you that you shouldn't build a new authorization language. So before we built Cedar, what we did is looked at the space of existing authorization solutions to see if we could reuse one of them. What we found is that they fall broadly into two categories. In one category, you have languages and engines which are very expressive. They let you express arbitrary authorization models. So you can, instead of sticking with a standard one, RBAC or ABAC, you can define your own and encode it in these languages. Now that's cool, but the problem is that because they're so expressive, you can't bound performance and you can't analyze them. On the other hand, you have a class of languages that are very fast. They're extremely performant, and in principle, it will be actually fairly easy to analyze them. The problem is that they're not expressive enough. They will let you write RBAC rules and some other flavors of RBAC, but you can't write ABAC rules. What was missing in this space was a language like Cedar that balances these competing concerns of expressiveness, performance, and analyzability. So what we're going to do now is look at how we build Cedar, starting with the language design. We built the Cedar language by working backwards for customer use cases to define 3 main requirements. I will illustrate what these requirements are on yet another example of what Cedar can do, and in this case I'm going to use a cloud-based photo sharing app. In an app like this, a user like Jane might want to upload her photos to the cloud. She will want to tag them, and she will want to organize them into albums. She also wants to share photos with individual users and groups of users based on how they related to her. For example, Jane might want to say that all of her friends are allowed to access or view and comment on all the photos in her arts album that have this nature tag and that are less than 2 megabytes in size. Okay? And as you've seen in Mahmoud's example, Jane would do this through some UI, and the application would convert these UI interactions into a permission policy that looks like this. Now, what does it take for a language to allow you to express things that are as different as a financial app, a photo sharing app, and a vet app, right? So the first thing that we have to be able to do is we have to be able to let you inject your own data types into the language, okay? So bring your own types, bring your own hierarchies, and bring your own attributes, all right? So the language allows you to do that, and you can use your own types. So in this case, entities that make sense in your application, albums, photos, and so on. And you can reference entities in your store by their identifier, right? Which takes the form of the type name and the name of the instance of the type. This is going to be some opaque UID in real life. We're showing nice UIDs on the screen here so you can read things. We allow you to use this in operator to navigate the hierarchies, okay? So the in operator determines whether the thing on the left-hand side is a member of the group on the right-hand side. This is how you express the RBAC rules. And finally, we also allow you to bring your own attributes, of course, and to access them within the policy using this dot operator, which is going to be familiar from a language like JavaScript or Java. So that's our first requirement. We let you, so these entities, these application-specific entities, hierarchies, and attributes are first-class core concepts in the language. Now, the other requirement that we have to satisfy is in most of our customers' applications when we talk to them, they told us that these attributes are coming from a variety of third parties, right? So think about a photo sharing app. Maybe the photo data is coming from user devices. So various kinds of third-party sources, but usually these are structured in some sort of data exchange format like JSON. Okay, so for you to be able to express your attributes naturally in our language, we support aggregate data types. In this case, the set is the aggregate data that we support, and nested records. So you can nest things arbitrarily the same way that you would in a JSON blob. Your mental model should be, I give Cedar my JSON blob, and it just runs. It understands how to navigate this, what attributes are, and so on. The final requirement, and is the one that Julian mentioned as well, is that the language had to be simple to read and write. This is both for the purpose of authoring policies and auditing policies. You shouldn't have to read a manual in order to understand what a policy says. We accomplish, or we satisfy this third requirement by organizing our policies into 2 parts. An RBAC rule, followed optionally by 1 or more ABAC rules. So the RBAC rule here is shown in green. So this is the head of the policy and the scope. And the only thing that can appear in the head of the policy are these hierarchy constraints, okay, using the in operator and the equality constraints. That's the only thing that can appear there. You constrain the principal, action, and resource using equality or in. And if that's all you need to say, that's your RBAC rule, or you're done. If you need to constrain access or permission some more, you will use an ABAC rule, and you can use any number of them. I'm just showing 1. What goes into this ABAC rule, or we also call it a condition, is an arbitrary Boolean expression in the Cedar language. You can think of this as a pure functional subset, loop-free, no side effects, no mutation of a language like Java or JavaScript. So that means you get all the constructs that you're used to, right? You get ands, or, nots, conditionals, and the operators on your primitive data types. Now, another thing that you can put inside of this condition, but I'm not showing here, is also hierarchy constraints and equalities, which brings us to the obvious question. If I'm allowed to put hierarchy constraints in my ABAC condition as well as my RBAC condition, what is the point of splitting the policy this way, right? Why didn't I just give you this alternative, hypothetical, monolithic syntax for expressing policies in the language? Any guesses? Yes. Wow, fantastic. See? So the first answer is readability. We actually asked our customers, we presented with both syntaxes and said, which one do you want? Which one do you like better? Which one do you find more readable? They prefer the structured one. And the reason is, with a structured one, you can just glance at it and see what's going on, right? It's an RBAC rule followed by an ABAC rule. With an unstructured one, you as the human being have to pretend to be a parser, right? You have to visually parse the policy and then extract parts which are ABAC rules versus the parts that are RBAC rules. So that's one reason. The second reason is that if you write your policy this way, your evaluation, policy evaluation, is going to be much more efficient. The reason is that we designed Cedar to have a property called slicing. This property means that it is possible to correctly evaluate an authorization query against a small subset of all the available policies and all the available data in the data stores, and get the exact same authorization result, including errors, actually, including error messages, that you would get if you were to evaluate this request against the full store. So what we do under the hood is we're using the head of the policy to create indexes, which allow us to quickly compute the policy slices and make fast authorization decision. So the syntax is designed so that it nudges you toward writing policies that are more readable and more performant. Okay, so that's how we designed the language in a nutshell. And let's talk about how we built the engine. From the point of view of client of Cedar, you know, AVP is the client of Cedar, it takes three inputs. The request, so principal, action, resource, and context. Entity slice, so some part of your entity store, and a policy slice. And it passes these inputs to a module called the authorizer. The authorizer runs the evaluator on each of the policies against the other two inputs to obtain one of three results, true, false, or error. And then it combines the individual policy results into a single authorization output, allow or deny, along with the diagnostics that you have seen in the previous slide that Mahmoud showed. Now, the first question that we're going to tackle is, how does Cedar achieve speed? Okay, we have to achieve both speed and safety, so let's tackle speed first. We achieve speed by building Cedar in Rust. Rust is a high-level language with the performance and memory characteristic of a low-level language like C. Okay? Cedar is blazingly fast. To give you an idea, a typical authorization request involving hundreds of policies and thousands of entities takes less than a millisecond. Cedar is very memory efficient. The reason is that Rust doesn't have a garbage collection or any kind of a managed runtime. The Rust compiler proves, if your program compiles in Rust, it type checks, the Rust compiler proves that it's free of memory safety errors. Okay, so by building in Rust, we get speed and memory safety. But how do we get correctness? Okay? How do we know that this engine that we implemented is actually correctly implementing the semantics? Well, a programming language alone can't give you that, so we have to do something extra. The extra thing that we did is developed a formal executable specification of the Cedar semantics. This specification takes the form of a very small, high-level functional program. It's only 500 lines of code. You can sit down and read 500 lines of code in an hour and convince yourself that it corresponds to our English spec. Now, to check that this reference implementation matches the production engine, we use a technique called differential random testing. This involves running both engines on millions and millions and millions and millions of inputs until you achieve coverage of the production engine. And you make sure that on each of those inputs, the two engines produce the same authorization result. This gives us high confidence that the production engine matches the semantics of the language as embodied in the reference engine. Now, here's the really cool part. Our reference engine is built in Dafny. It's about 500 lines of Dafny compared to about 10,000 lines of Rust. Dafny is a language, programming language, that has a built-in theorem prover and a verifier. What that means is that for all those properties about our language semantics, such as slicing, we can construct a mathematical proof that those properties hold, and the Dafny verifier will mechanically check that our proof is correct, that all the logical steps that we specified do in fact hold, and the antecedent leads to the consequent, right? Some example properties that we have proved are shown on the slide there. So the properties that we care about have to do with security. So forbid, permits, overrides, permit, right? We have proved that for any policy that you can throw at us, doesn't matter what it is, we've never seen it. For any inputs to that policy set, if there is one that says forbid this access and the other one says permit this access, forbid is going to win, okay? So that's a key security property that we have proved. A key performance property that we have proved is that slicing property that I mentioned before, that it's actually okay to make this authorization decision against a small slice based on these indices as opposed to the entire store. So by using Dafny and by using Rust and differential testing, we have high confidence that our production engine matches the semantics and that our semantics has the properties that we care about. So this brings us to the last part, which is the static analysis tools that you, as the policy author, get when you use Cedar. If you sign up for ADP today, you will get out of the box a powerful static analysis, which we call validation. The validator is based on an advanced type system. It will check that your policy is free of many kinds of runtime errors, including, of course, type errors. What we're working on right now, so this is a sneak preview, is an even more powerful kind of analysis, which is based on satisfiability modular theories or SMT solving. These kinds of analyses allow us to answer universal questions about policy behavior, and to do so quickly and precisely. In particular, if you give us a property that you want to make sure your policy satisfies on all possible inputs, the underlying solver can quickly search an immense state space, okay, infinite in the worst case, and make sure that your policy does indeed satisfy that property on every single point in that space. If you have this underlying infrastructure, you can build very powerful policy authoring tools. Let me give you an example. We can build a set of tools, we call them an equivalence analysis. Actually, we've already built them, we prototyped them, that allow you to refactor and optimize your policies with confidence. What does this mean? This tool will make sure that any changes that you make to your policies will not either increase or decrease the set of things that are allowed. Okay? So you're not going to mess up. The tool will tell you if you mess up. So here's an example. What you see on the slide there, and I'm not expecting you to read those policies, by the way, is a set of 3 policies from that photo sharing application example. Now, this is the kind of state that you might get in if you're iterating on a new app, right? So you have different developers figuring out who needs to be accessing what, and they just keep on adding permissions and, until things work. So now imagine that an auditor is coming tomorrow. So these developers have to refactor this into something that the auditor can easily examine and convince themselves that it's doing the right thing. If you had time to stare at this for maybe the next 20 minutes, and we don't have that much time, you would see that these policies are actually saying something very simple. These policies are saying that a principal can view or comment on any resource that they own. It's fair enough, right? I can see my own stuff. Or on any non-private resource that is a JPEG or a PNG photo that's owned by somebody else, okay? So that's all these policies are saying. Now let's say that we want to refactor this and replace it with a much simpler policy that kind of follows the structure of the English sentence, all right? So here's an attempt to do that. And it sort of looks like it's following the structure of the English sentence, right? It's saying that allow things when resources in principal's account, when the name has the given shape, unless the resource is private, right? So it sounds like it should be right. We can ask the analysis to check whether this is true on all possible inputs, right? So what the analysis is going to do is going to examine the universe of all inputs that could ever come into your policies and see if these two policy sets agree on all of them. In this case, the answer is going to be no. I made a subtle mistake when I did this refactoring, and the analysis is going to synthesize a concrete witness, a test case, right? A request and an entity store, such that if you were to run this request against this synthesized entity store, you would see that the old policy set permits this request while the new policy set does not, okay? So it's found a bug. Now, there are many ways to fix this particular bug. I will show you the simplest way, which is to just split this into two policies which correspond to the two clauses in that English sentence that I have. The first policy deals with the case when you own the resource, and the second policy deals with the case when you don't know the resource. And when we run the analysis again on these two sets of policies, it's going to say that it's okay, and you're done. Now, equivalence is just one of example of the kind of policies that, or the kind of analyses that we can do with the underlying technology that we are currently building for the Cedar language. And if you have ideas for the kinds of analyses that you would like us to build and run your applications, please do reach out and let us know. We would love to hear about it. And with that, I will hand it back to Julian.
Thanks, Amina and Mahmoud. So that wraps it up for the day, for us anyway. You can see here a QR code which will take you to the landing page for the service. There are a number of resources out there online. There's a website that we've set up that is dedicated to the language itself with a set of tutorials and an overview of the language. And we'll be obviously publishing more resources as we go forward through the rest of this year and into next year. Thanks again very much for coming. We launched a gated preview. So if you have a project in mind that you would be interested in using this service to try out and build against, then sign up for the gated preview. And the three of us will be in the anteroom afterwards. If you want to follow up individually with any questions, we'll hang around for a while if there's anything you'd like to chat about. So again, thank you for your time and enjoy the rest of the show.